Thank you. I didn't do anything yet. Very nice of you. Welcome to my talk, Unsafe for Work, or I'm going to try Italian now, non sicuro per il lavoro. And I hope I got that right. That's all the Italian that I have in me. Okay, so before we start, I want to, we're in the city of art, we are in Florence. I wanted to bring some beautiful imagery to the city. So if you can take a look at this particular image here, it's the cover of a book. It's a computing book from the early 90s, released in Germany. And I bought this book about a year ago, around Christmas. I'm getting back to that image a couple of times, but take a look, let it sink in, try to grasp what it's depicting. You might see that there's a knight with a cape and a big bushy mustache, a buffalo, riding on top of a dragon, which has a very friendly face. And there's lots of animals around there and a castle in the background. What could that be? I give to you 1 or 2 seconds. C++. Oh, you have no idea. All right, cool. What's the deal with Unsafe, right? I mean, Unsafe Rust has caused so much confusion and so much discussion in our community and everywhere else. So it confused me a lot, that's for sure, but also if I talk to people about Unsafe Rust, it seems that there are lots of misconceptions around this topic. And I'm here today to clear a couple of those misconceptions. And since it's called Unsafe for Work, it's not only a nice title, I also will tell you how we, at our work, where I work at Dynatrace, deal with unsafe code. And you know, this is what people at, for example, Reddit say about Unsafe Rust. And I love that people are very unsure about that, and they ask really, really good questions. One particular posting that is legendary, I guess, if you are a regular follower of that subreddit, is, should we be worried about proliferation of unsafe in Rust codes? Because the poster highlighted that there are many occurrences of unsafe in Rust. Vector is full of it, and even popular crates like Rayon have 147 occurrences of unsafe Rust in them. And Azul has 3,680 occurrences of unsafe Rust in that. And I particularly like that the poster used the term proliferation, which means like wild and uncontrollable spreading of things. And in German, the German equivalent Proliferation means the distributions of weapons of mass destruction. And that's unsafe for sure. And I love that the imagery that it gives to you if you really want to deal with unsafe code. Another poster said, is unsafe Rust just moving the problem? And one poster is worried that unsafe Rust makes Rust an unsafe language altogether. So what's the deal with all the memory safety if Rust is unsafe to begin with? And then there's one excerpt from a talk that I heard last year. It was at the German Rust conference, and the keynote speaker gave an introduction to the memory management and memory system of Rust. And what they said was, well, if you use unsafe, you can turn off the borrow checker. He said it in the slides a little bit different. It bypasses the borrow checker completely. Well, this is not entirely wrong, but also not right. And this was this one particular posting that triggered me to research more about Unsafe Rust, to see what it's really about, and to ask the question, for example, does Unsafe Rust really deactivate the borrow checker? First of all, little spoiler, the answer is no. That's the biggest no that I could put up on a slide. I would have used the Italian no, but it has 1 letter more. So this is the biggest no that I can do. Unsafe Rust does not deactivate the borrow checker. If we use it like that, well, let's see how our borrow checking rules still hold up. So this is a function called split over a slice of t, of a generic type of t. And what it does is it takes a shared reference of the slice and creates 2 sub-slices split at this one particular point that we pass as another parameter. So we have a slice from the beginning to point and then from point to the end. Easy stuff. If you want to create a mutable version of that, split mut over a mutable slice of t, and we want to get 2 mutable slices in return, if we do it the same but just have mutable references to it, Rust will cause an error at this particular point. And it will tell us, well, we have a second mutable borrow that occurs here. You can't do that. That is not aligned with the ownership and borrowing rules that the borrow checker controls. So far so good. This is what we expect from Rust's memory management, memory checks. So if we would just put unsafe around it, an unsafe block with those curly braces, if unsafe really bypasses the borrow checker completely, then this would work, right? Well, no, we get the same error at the same position with the same error message. So it still tells us you have a second mutable borrow, you can't have a second mutable borrow. This is not what the borrow checker allows. So unsafe deactivates the borrow checker. That's fundamentally wrong. That's not the case. And for some reason, this image comes into my mind again. So I don't know if you recognize the dolphin. This is kind of weird if you have this medieval setting with a castle and a hero on a dragon, and then you have a dolphin jumping out of the water and looking friendly towards you. So that's interesting. OK, unsafe Rust again. So if unsafe Rust does not mean that you just unplug the safety belts and can do whatever you want, what does it mean? And the best way to describe unsafe Rust is to think of it as a language superset. This is also what you find in literature and books and documentation out there. Think of it of a language superset that gives you more capabilities. This is directly from the documentation. Unsafe Rust allows you to dereference raw pointers. We are getting to that, to call unsafe functions and methods, and I think personally those are the most important things that unsafe Rust can do. All the other things can still occur, like mutating static variables or implementing unsafe traits. Guess what? Or accessing unions, which is a data structure that mimics C unions, and you need that for interfacing with C. But from the project that I've been involved with, dereferencing raw pointers and calling unsafe functions is actually the thing to do, and I want to focus on that. The first thing in that list, raw pointers. So there are a couple of pointer types in Rust, and those are 3 pointer types that you already know. It's the own type, the reference, and the mutable reference, a shared reference and a mutable reference. And the borrow checker checks on those pointer types. Shared references and mutable references are also called shared borrows and mutable borrows. And shared and mutable borrows are checked by the borrow checker. That's what the borrow checker does. It checks those borrows. So this is a nice bridge, if you like. The borrow checker still works on those particular type. Unsafe Rust introduced 2 more pointer types, constant and mutable raw pointers. The type is denoted with these little asterisks over there. And those pointer types are no borrows. They basically do the same. They point to some address in memory where there's a value. But they are not checked by the borrow checker. Those are unchecked pointer types. And the main difference is that they don't have any lifetime attached to it. The borrow checker could check. So they don't have any lifetime. Therefore, the borrow checker doesn't work. The borrow checker can't figure out if they live long enough. How do you create a raw pointer? There are many ways to do that. I recently stumbled upon this new syntax introduced in Rust 1.80, where you can have this ampersand raw keyword, where you can create either a const raw pointer or a mutable raw pointer. I pointed to the first element in this array of 5 values. And if you have an overpointer in your editor, you can see the type. It's an asterisk const i32, a constant raw pointer. There are other ways, like casting it to a const pointer, or using the sPointer method that is implemented in many types, or sPointer mute method that is also implemented in many types. So what is a const raw pointer? Well, it's what you would expect. It's some address and it points to some data. That's a const raw pointer. If we take this pointer and print it out using the debug trait, you get a beautiful, you get a beautiful address. What you would expect from this notation and from other languages like C and C++. And this bears the question, is this all just C and C++ all over again? Some folks on Reddit might suggest that. You know, you have those pointer types, you have an address to it, so maybe it's the same thing. Well, let's work a little bit more with them. So in this example, I create a mutable raw pointer in the beginning from this array, and on line 3, I dereference that pointer and change its value to 9. So instead of 1 at the first entry of v, it should be 9. And then I want to print it out. And this doesn't work in Rust. So if I compile that, I get an error at this position and at this position, and the compiler tells me, rightfully so, that v dereference a raw pointer, and raw pointers might be null, might be underlined, and might be dangling. Sorry, yeah. Might be dangling as well. This is the unholy trinity of undefined behavior, basically. This can cause undefined behavior, and in Rust, you are not allowed to just dereference them like that. If you want to make that work, what we need to do is add the unsafe keyword around it, create an unsafe block around it that allows us to dereference raw pointers. Now this program compiles and does what we expect it to do. Change the first value of v to 9 and then print it out. This unsafe block does not shield us from unsafe code, but it highlights unsafe code and makes us aware that bad stuff can happen here. Like this, for example. So this is my dangling pointer example, and I like that I had a little Freudian slip in there by calling it dangling pointer. So this happened completely by accident. I create another pointer, PTR, and then I have a block. I have a block on some value, 42, and then I create this cons pointer. And since this value lives just in this particular block, hence the ownership rules, it will be freed at the end of the curly brace before calling the unsafe block where I want to dereference that pointer. The pointer still points to an address afterwards, but we don't know to which value. So if I print it in debug mode, funnily enough, the result is still 42. If I run it in release mode, I get any other number. And this was just on that particular day, at that particular time where I ran the example that I got, what was it? 2, 4, 5, 6, 5. If you like to implement random number generators and need seed value, perfect, but I guess there are better ways to do that. And this is what we understand also as undefined behavior. Rust can guarantee that the values are what we expect them to be. And that's what unsafe blocks allow. Unsafe blocks allow to dereference raw pointers. They allow us to call unsafe function. We are getting to that, which in turn might dereference raw pointers. And for you as a developer, this means that the compiler does not check the code for you if you work with those pointer types. You need to make sure that the safety conditions and precautions that are necessary are in place and are met. It's your duty now and your responsibility. You can think of it like, here are dragons. So this might be a nice emoji keyword for the same thing. If you see the dragon, be aware something is happening. Talking about dragons again. So I kind of come back to this particular image where you see this dragon. It looks so friendly. It's really cute, actually, for a dragon. Not just because of the comic depiction, but actually it has cute eyes, doesn't it? For it. What I don't get is this beaver with the life buoy. So I don't know why this one is here. And it also doesn't fit to this medieval setting. Okay. We've seen unsafe blocks and unsafe functions. Let's talk a little bit about them in the next block. So there are unsafe functions. That's a function with the unfixed prefix in front of it. And this prefix highlights that code inside this function might cause undefined behavior. This does not necessarily mean that this code dereferences raw pointers. This does not necessarily mean that this code includes unsafe blocks or calls to other unsafe functions. All it does is that it tells you that if this code is executed, you need to make sure to care about certain safety preconditions. You can, for example, decrement the length of a vector or something like that, which would not be unsafe to begin with, but which could cause unsafe behavior elsewhere. This is why you would mark it as unsafe. On the other hand, you have unsafe blocks, and unsafe blocks highlight that if you have certain safety conditions that you need to meet, put them inside this unsafe block. Those are the contracts that you get as a developer. If you want to call that stuff that needs preconditions being checked, then call them inside this unsafe block and check those preconditions accordingly. And with that, unsafe moves those safety checks from the compiler to the developer. And suddenly, they become your responsibility. And it becomes your responsibility to check all those safety invariants. That's a term that you hear a lot. And I think the most important thing about that is that it makes those things explicit. And Rust is really, really good at making things explicit. It's a very explicit language. Who in here has used unwrap? Yeah, okay, every hand should rise now. Of course you did. So this is the shortcut. If you know that the value is there, just unwrap it and work with it. Ed just gave a beautiful example this morning where unwrap was used a couple of times and what it means. But it means that we ignore the error case. So we ignore the not existing value. But we ignore it explicitly. It's our conscious decision to ignore it. And if we go back to the code in the future, we still find those occurrences and know where we ignored it. And I speak from experience because we have written a 50,000 lines of code Rust application, and we had 151 occurrences of unwrap in there. How do I know that? Because I was able to search for it in plain text. And this is great because we had one developer and they used unwrap everywhere, and we didn't have any code reviews in place or whatnot. But we were able to mitigate that problem by searching for the keyword with a plain text search. And the same thing applies to unsafe. Use unsafe very explicit to highlight those places where you are dealing with code that could cause potential problems. And with the introduction of this unsafe block and those unsafe functions, it becomes totally clear where this behavior is happening. And this, in my opinion, is fundamentally different to how pointers and unsafe code work in C and C++. So is it C and C++ all over again? No, I don't think so. You just have very few means to cause undefined behavior, and you need to highlight them accordingly. Compare that to a C and C++ code base where you have pointers all around and everywhere. Again, for some reason, every time I debunk one of those myths or misconceptions, I come back to this image. Anybody figured out what it means? We're getting to that. So if we want to work with unsafe code, one thing that really helps with that are safe abstractions. One thing that we need to accept is that we can't avoid unsafe to begin with. Really, we can't. The standard library is full of that, and that's okay. There are situations where you need raw pointers. That's how those data structures work. That's how, in a way, computing works. But it's possible that we avoid working with unsafe code entirely, and we can do that by using safe abstractions. I want to take a look at Bevy, an immensely popular game engine and Rust library poster child. Francois, is he in the room? I don't know, but Francois gave a workshop on Saturday on Bevy, developing games with you, fantastic. And Bevy uses a lot of its own data structures and therefore includes also a lot of unsafe code. Originally, I had a different example in there from the expressive crate, but after I saw Boxy at Eurorust showing a couple of those abstractions, I thought, okay, this is much, much easier to grasp and gives you a better understanding of what those safe abstractions are actually about. I sanity checked it with Francois, which is one of the great things of being at the Rust conference, to get the hands on them. This is a thin array pointer. I just focus on the release part code here, so if you open the create yourself, you see that there's lots of debug information sprinkled in and lots of debug assertions sprinkled in, but I just focus on the release mode code. And thin array pointer is a Bevy structure that works like wreak of t, but it cuts out length and capacity for performance reasons, which means that you allocate some memory, you work in it, and then you drop it. No reallocations, no bounce checks, nothing. You have this slab of memory, do your stuff, then throw it away. And it has a pointer to some data. And this pointer is a non-null of t. This non-null of t is also already a safe abstraction to a mutable raw pointer. Inside it uses a const pointer, but then it adds mutability on top of it. And the documentation says that it is non-zero and covariant. Non-zero means that there's actually some memory underneath that pointer. It's not non-zero in the way that there's not a zero value allowed, but it's non-zero in a way that it has some length to it. There are spikes underneath. And it's covariant, which means that, I mean, covariance is a topic in type systems that makes for its own talk. For our case, it means that it has lifetimes attached to it. And those lifetimes work like you would expect them to work. Which means that once we have that safe abstraction, this non-null of T, ownership and borrowing works again. And that stuff is being checked again. Okay. When we look at the impl block, the first method that comes into mind, and this totally violates Ed's coding guidelines because it's the helper function before the actual function. You have this method called empty, which creates a thin array pointer where non-null is still a dangling pointer. If you look at this non-null dangling function, it tells us that it creates a pointer that is dangling but well-aligned. Well-aligned means that the address this pointer points to is dividable by the bytes it takes for T to being stored there, which means that you get one address where you can store the whole thing, and if you have multitude of those, every offset hops the same number of bytes. Non-null dangling even says that it's useful for lazy allocating types, like vectors, so that's exactly what we need. And if we look at the code, give me a second. I can't find my cursor. Whoop, whoop. Oh, fuck it. And if we look at the code to it, we see that non-null dangling itself has an unsafe block in it. So this is a function, a safe abstraction on top of some unsafe code. Because we have this new null, colon, colon, new unchecked with a pointer. So first we create a pointer, and then we initialize the non-null pointer type. And this is an unchecked function. This is an unsafe function. Stuff can go wrong here if the pointer is pointing to nowhere. But the line above, this create pointer dangling mute, make sure that the pointer points to some data. The unsafe block tells us this is step one. We create a pointer that points to something, and then we create this non-null abstraction that calls an unsafe function, but all the preconditions are met. And this even is being said by the comment in front of it. It has this safety notice that tells us what were the preconditions, how did we meet them, and this is why this particular call of unsafe code is actually safe. This is beautiful. And that's just 3 lines of code, and everything in this code is clear and understandable and tells us what's going on. And we see something similar if we look at the function with capacity. This is how you create a real theme pointer array. First, this function creates self colon colon empty, which itself also called some unsafe functions. Then you check if the capacity is bigger than 0. And if this is the case, then you allocate some memory with a method that is built in this thin array pointer. The funny thing is that we use, or Bevy uses a non-zero usize, new unchecked function. Again, this is an unsafe function because if you create a non-zero usize with 0, stuff goes wrong. This is why it's unsafe. This is why we need to wrap it in an unsafe block. But we check all the safety preconditions. We check that if the capacity is bigger than 0, then we create a non-zero usize that is, well, not 0. This is what it does. And again, it becomes totally clear what the precondition is. It becomes totally clear what we need to do to meet this precondition. And we have it in just 1 line of code, maybe 2 or 3, that tell us what's actually the problem that could cause undefined behavior and how do we mitigate them. Here's the documentation. It tells us, well, this value must be not 0 for non-zero users to be created, and it is an unsafe function. So I would argue, yes, there's lots of unsafe code involved. Bevy just had 1 occurrence right now where they needed to use the unsafe keyword themselves. But if you go down the call graph, down to all the data structures being used, to all the abstractions being used, I'd argue there are lots of unsafe occurrences. And this is why, if we remember that posting about the proliferation of unsafe in Rust, this is why you see so many times the unsafe keyword, because you reduce the usage of unsafe to a few lines of code where you can make really, really sure that what you do is actually safe, where you can check all those preconditions, where you can make sure that all the safety invariants are being met. And I would argue, even if you use unsafe code there, everything that you've seen so far is safe. There are some safe abstractions that you have used. That's the unsafe police calling. I'm pretty sure every one of you has wreak of t. Maybe every one of you has used all of those abstractions that you see on that slide. Wreak of t is full of unsafe code because it works like that. You need to find a pointer, you need to allocate some memory. When you go over the capacity, you need to reallocate, which means you need to call a lot of allocation functions that are unsafe code. Or if you use a string can be represented as a vector of characters. And if you open up the string implementation in Rust, it's exactly that. It's a vector of characters. Of course, this uses some unsafe code underneath, somewhere deep in the call graph. And you know how other memory-safe languages are doing that, like Python and JavaScript? They give you safe abstractions. They give you a safe object. They give you a safe array. And this safe object or array is implemented in C and C++ in a safe way, so that all the safety variants are being checked. And I guess there's one JavaScript engine out there that has 17 different implementations of string, depending on how you write the string in JavaScript. That's a lot of string. That's a really complicated data structure. And it works safe. Unsafe Rust is kind of the same thing. The only difference is that you have your safe code and your unsafe code next to each other. And you can hop into the unsafe code and can hop out of the unsafe code. But in reality, it's like working with a totally different language that has nothing to do with the safe Rust that we know. All right, this talk is called Unsafe for Work. So how do you use unsafe code and unsafe safe abstractions in your day-to-day code? First of all, you are fine, really, relax. The chances are that in your project, you won't be bothered too much with it unless you use dtrace and have all those unsafe ASM calls in there that I saw from the presentation yesterday. But most of the time, the chances are that you won't be bothered with unsafe code at all. If you think, or go back to the beginning, we saw a couple of things that unsafe Rust enables, mainly dereferencing raw pointers and calling unsafe functions and methods. So what do we need that for? And I found out there, in my experience, 3 particular use cases where this is really, really handy. First of all, hardware access. If you're writing operating systems or work with embedded devices, it's really, really good to access this particular address directly. And you can take an address and call it to a pointer and dereference and work with it. Then foreign function interfaces. If you interface with C and C++, that's what we do at Dynatrace, well, then everything that comes from C++ is unsafe. Also in Rust. And you need to handle that in particular. And if you are a library like Bevy, if you want to do some more performant data structures, if you have the need for that, then Unsafe Rust can help you there as well. This doesn't mean that Unsafe Rust is more performant than Safe Rust. That's not the case. If you need to manage all your own, the compiler can't do some optimizations there, but you have the potential and possibility to write more performant data structures. So not a lot of use cases where we see that in the wild, but to be honest, also some very important use cases. If you interface with C and C++, hey, we want everybody to migrate from C and C++ to Rust. So this happens a lot. And if you look at migration stories from C and C++ to Rust, well, that's what you get. You get lots of unsafe code that you need to wrap in safe abstractions. Also, we want people to write embedded code in Rust. So also here, you get lots of potential to interface with Unsafe Rust. This comes from a real-world project. This is our JavaScript runtime. So next door, there's Leo's talk. He tells you how to integrate the Deno crate in your Rust library. That's what we do. We have written our own JavaScript runtime based on lots of work that the Deno folks have done. I mean, if this is statistics of how many lines of code we use for that particular project, and if you ask, hey, in what language have you written it? Well, all of them, apparently. But the mainstay is written in Rust, about 50,000 lines of code. And we have one single occurrence of unsafe code in there. And that's this one. We use the Rust v8 crate. It's a safe abstraction interfacing with all the C++ interfaces from v8, from Google's JavaScript engine. There's just one thing that it doesn't do, which is if the whole thing crashes down horribly, it produces an error string. And we get a pointer to that error string. We know that this error string is always there. And then we can serialize it from a pointer to an actual C string and work with that. That's what we do here. And we do it in the right way. We have very few lines of code inside that unsafe block. We checked all the preconditions previously, even if it says assumes, but no, we know. We know that we always have a valid string pointer, and we have the safety comment in front of it, telling us what we did to make sure this particular code is safe. It's beautiful. How did I find that? Well, I've not worked in this code base for 2 years now. I just looked for Unsafe and found it and knew everything that has happened. Because we followed a couple of code guidelines. First of all, we limited our use of unsafe code. Okay, that's what we did. We paid attention when we approached unsafe code, knowing that all preconditions are met, and we documented what's going on there. Every time you deal with unsafe code, you see those / safety blocks. They are a lifesaver. Be very elaborate when writing those. Be very elaborate when reading those. So make sure that everything that stands here is actually true. And it makes safety environments very, very easy to search for. This was just one occurrence in a pretty big project. And I spoke to a couple of people. Yeah, at times you have some unsafe code that you want to use. But I loved it coming from this one particular post in one of the threads from those Reddit posts I've shown you earlier, because some user says that people think that if you write low-level code where you work with microcontrollers, operating systems, whatever, that you write all that code in a huge unsafe block. And that's not the case. They are working with a microcontroller where they haven't written a single line of unsafe code, even when accessing memory directly. And that's because they use this ESP IDF SVC crate, a first-party crate from the Espressif folks for the hardware, safe abstractions for the hardware, and this is excellent. And this is what we need. We need more of those things. We need safe abstractions coming from first parties that make interfacing with this hardware easier. That's the same thing we did with Rust v8. The Deno folks took on the toll of abstracting the entirety of v8 of Google's JavaScript engine to safe abstractions in Rust that we can use. This is amazing. It's not first party, but we take third party. That's fine. And it helps us a lot in doing our day-to-day work. Little look at the dangling pointer example. If you write your own code, one thing that you can do to have extra safety checks if your code is sane and next to being aware that stuff could happen is running Miri. Miri is an idly add-on that takes the mid-level intermediate representation of Rust and checks if there's any potential for undefined behavior. And if I look at this dangling pointer, if I run it with Miri or build it with Miri, I get an error. It tells me, wait a second, this is out of bounds. This allocated memory has been freed. This pointer is dangling. It won't compile, which is great. If I look at the split mute function, a little bit different. I now use a method as mute pointer. If I run this from Miri, Miri is very happy with me. This doesn't cause undefined behavior. Let's cause some havoc. What if we take the same example like earlier and move the index here, -1, like, oh, now I have a little overlap, so I get 2 mutable slices, but the last entry of the first slice is also the first entry of the second slice. So if you change something in the first slice, then something happens in the second slice as well. So this is not what you want to have. It's a lot of fun, but it's not what you want to have. If I run Miri on top of this code, what I get is another error message. It's great. It tells me that the same memory has been tagged twice. And this is not allowed because memory should have the unique permission for just one of those bindings. It tells me exactly what's happening there, and this is so great. So if you have your own safe abstractions on top of unsafe code, test them and run Miri, and it helps you a lot. Miri helps identifying undefined behavior. It can't find everything, but it can find a lot. One caveat is that it's highly dependent on the target architecture that you've been using, but it's a really, really good start. And it gives you sanity checks for that little piece of unsafe code that you write. So we know that unsafe Rust is a superset in the Rust language, and it allows things that safe Rust won't allow. But I think the only difference to other memory safe languages is that you can write both safe and unsafe code in the same file. How many C code is there in Python that you use indirectly? Tons. Every machine learning library has lots of C code underneath. Here in Rust, we have it in the same file, and we can find it very, very quickly if we use something that might cause undefined behavior. It highlights stuff explicitly. It highlights potentially problematic places in your code, and you need to declare everything accordingly. And such, I would think that unsafe is actually a safety feature. It makes finding those things much, much easier. And if something goes wrong, you know where to look at. Unsafe Rust is not about giving you all the freedom that you have with C and C++. It's about highlighting and preventing undefined behavior. It gives you a little bit more responsibility for your code, so Rust can ensure that the rest works as intended. OK, you remember this one here? Any ideas what this could be? You have a hero with a cape and a big bushy mustache on top of a friendly dragon, and he wants to save a princess. Exactly, fantastic. It's the German strategy guide to Super Mario World, released in the early 90s. And it's beautiful. The thing is, not even generative AI could mess it up that much, and I love it for that. So I enjoy this picture truthfully a lot. But, you know, think about the artist. The artist clearly had a different thing in mind than we do when we work with, when we think about Super Mario. He had a totally different view on that. He might have heard about those stories. Maybe he saw some images from the game and he said, yeah, sure, hey, you have this mustache guy with a cape. He rides a dragon. He rescues a princess. There you go, medieval setting. Fantastic. He didn't know that Mario is a plumber or that you jump on turtles or something like that. But the point is, this artist saw what he was familiar with, missing the point entirely, creating a false, misguiding representation of something that is clearly something entirely different. And I think this happens when we talk about unsafe Rust as well. When we talk about unsafe Rust and we see this little asterisk in front of a pointer pointing to some memory, and we can print it out and get some memory, and can do memory allocations with it, using all those functions, somebody who has worked with C and C++ a lot might get the same idea that unsafe Rust is just the same thing as C and C++, when it's not. They focused on a couple of details, yes, and they are, by design, very much alike. I think it has been a conscious decision to design a raw pointer with that asterisk, to make, to create this similarity to C pointers, but it's something entirely different. And that's all I wanted to show. Thank you very much for your time. Thank you very much for being here. No game over slide for me. I had 10 seconds, I guess.
Yeah, we finished like 2 minutes early, so
cool, great.
Any questions? Don't be shy. Oh.
Would it be fine to show the slide with the no again? I would like to use it as a meme template.
Which one?
The slide with the big no.
Ah, yeah, sure. Of course. It was very early, wasn't it? Yes. That's peak typography. Here. That's actually the slide I spent most time on.
Yep.
Do you want want to have a meme from the Mario image? Or? Yeah, okay.
So if you see the picture on the left one,
yeah,
mushrooms
should it go to the Mario thing? Yeah, so there's, give me a second. It's been a huge presentation, hasn't it? So, going from the first slide to the last slide. There's lots of stuff that doesn't make any sense there. Because, you know, we are a couple of retro gaming nerds, and we try to look on what's happening. You see a mushroom is missing? Yeah.
Yeah, and eyes. So.
Yeah, but more importantly, there's a couple of things in there that don't make sense. The dolphin makes sense. There are a couple of levels in Super Mario World where you can hop on a dolphin and you need to go to the exit. The parachuted turtle makes sense. The albatross in there only comes when you beat the entire game, and then there are a couple of bullet bills will be changed to albatrosses, but that's post-game. Nobody knows where the beaver comes from. Nobody. It's a beaver in a life, but nobody knows where this one comes from. We checked the entire enemy catalog of all Super Marios that have been released until that point. There is no beaver in a life boy swimming in some lake or what. So, if you know, please tell me. Maybe that's a Goomba.
Don't you get that beaver tail?
Huh?
Don't you get that beaver tail?
Yeah, that's a raccoon tail. There's, huh?
It's a Mario Tanuki.
Say again?
It should call be Mario Tanuki, the one.
Yeah, exactly, yeah. Okay, are some questions on Unsafe?
Thank you. Thanks for the talk. It was very interesting. It might be a bit of a naive or philosophical question, but
I love philosophical stuff.
do you think there might be a world in the future where we don't need Unsafe anymore in Rust? Like having the compiler so powerful or Miri, that we don't need it anymore?
So I came to the conclusion that I don't bother if I have some Unsafe code in there. And therefore, I don't think we need a world where we don't have any unsafe code at all. Because, I mean, if you think about it, all we do is working with abstractions. And especially the one stuff that I showed you from Bevy. I have tons of unsafe code somewhere down the call graph. It's calling functions and functions and functions, and you reach one place where you have unsafe code in the end. And this is also just the abstraction on actually how machines work. So this is what you do if you allocate memory. You get that pointer to the data, you allocate that amount of memory that you do. It was very, very bare bones when we had C, because we called malloc and free. Yeah. And now we have hidden it under a ton of functions to do basically the same thing. And unless this changes how we malloc and free stuff, which I don't think will change, I don't think we will ever get rid of that. But we can reduce it to just a few occurrences where it's much, much easier to deal with. And I guess this is also one of the big problems that we had with C. You could do malloc and free everywhere. And then you need to have some sort of common understanding on when to allocate free. Do you do that within the same function? Do you give allocated memory back and you are the one that needs to free it? You need to document that stuff, or at least you and your coworkers need to design on some way of handling that memory. It was never about allocating memory and freeing memory. It was about composing all those different pieces together to create some software that in the end works. And we've abstracted it down to a couple of occurrences in those data structures, and the rest will be taken care of Rust memory management. And I think this is a really, really good way of taking care of that. And again, the only difference there is that we do it in the same language. We have somewhere deep down something like malloc. I guess it's even called memory_alloc something. And it works very, very similar to what you would expect from allocating that stuff in C. But it's deep down the call graph.
Okay, thank you.
Good question, Mary.
Any other question?
Thank you for the talk. We're gonna probably gain some more unsafe primitives, if we can say that, something like for the handling of provenance. We are probably going to have the unsafe pinned structure, to have aliasing mutable reference. Do you think that this could make the situation worse about the how unsafe is seen from outside, from people who generally don't use unsafe, and maybe they're more scared than ever.
So I think it has actually the opposite effect on top of it, because when I found out that Rust pointers have provenance, which means that you know where they're coming from, and it's attached to them, so they have an origin. To me, this means, okay, it's much easier to track down where stuff happened, which is actually the problem that I had with C when I had some pointer somewhere. Okay, where does it come from? What's the reason behind that one? And to me, personally, but I can just tell from my experience, this changed my perspective on the whole thing completely. So I think currently we have two possibilities. Either we ignore everything unsafe and focus on the whole safety features when you talk about Rust, or we highlight that, well, unsafe Rust has a reason, has a place in what we do, and we really think hard about how we can handle unsafe code, and we introduce all those features like provenance with pointers, etc., to say, well, this is not something that we take lightly. This is something where we actually spend some time on. I think it will increase confidence in the whole thing. And I think this is also something that we need to communicate. I've just shown you the postings on Reddit. The comments are really, really good. There are people discussing that honestly and with perspective and giving you lots of confidence that when you write Rust, that, yeah, there's unsafe code in it, but don't bother. It's okay. That's how computers work. But we managed to abstract it away from you. And what also helped me a lot is understanding that I've done 15 years of JavaScript. Can ask me anything. But knowing that underneath the JavaScript code is also just malloc and free down a different path of abstractions helped me understand the duality of the whole thing.
Thank you.
One of my biggest problems with Unsafe is that I'm afraid that the safety precondition of a function maybe would change in the future. So what do you think, like the safety, once you uphold the safety requirements, you can say that they will never change? How do you cope with that?
So I think the most important thing is to narrow it down to how do I say that? I mean, when will stuff change? When a certain API or a certain piece of your code does multiple things. And maybe it adds more things to it. Maybe the API changes for that, and suddenly you need to check on other invariants. The way all the functions from the standard library are designed, and also the abstractions that I know of, this is very, very little code. Very, I hate the term, but very single-purpose code. So the API design is in a way that it becomes really, really hard to add something to it or to change something once you want to guarantee some backwards compatibility there, which narrows the usage of that unsafe code and the abstraction that you write down to just a few lines of code. I think the best example is that one from Bevy where this pointer was initialized by creating an actual pointer and putting it to the new unchecked thingy. That new unchecked just holds the pointer. That's all it does. And the step above makes sure that the pointer is there. The API for new unchecked is clear. It just takes a pointer and it says, this better exists. And the other API says, well, I give you a pointer that exists. So you just put those two things together, wrap unsafe around it, and are done. There's little room for change in those APIs. And I think we need to design APIs like that if we want to produce unsafe code. If you are creating unsafe code where you say, hey, if you use that particular thing, make sure that the invariants that are to check are just a few. We're talking about invariants, which means, oh, there's a couple of things that could happen. Yeah, maybe it's just two things that could happen, or maybe just one thing that could happen. You know, boil it down to just a few things. and then you are not prone to any particular changes in the future. And I think this is a very, very good way to do that. This is also the reason why we have so much unsafe code in those libraries, because, opening unsafe, doing one or two things, closing it again. And this happens again and again and again and again. And instead of having this huge unsafe block where lots of stuff happens, you have little tiny unsafe blocks where all those things appear. Yeah?
Thank you.
Who's hungry?
Yeah, I'd say one last question.
Yeah. By the way, I'm here for the entire day and the entire night, so if you want to talk more, please do.
Thank you, Stefan. I found an error in your slide, which we can make one of your unsafe blocks even shorter. If you go back a couple of slides.
Was it the baby part?
Possibly. So this was also actually a style question. It wasn't, by the way, it's a comment. Hopefully we can find it.
That was baby?
Even further, we were, something like this, actually on the right. On the right, in the
this
box.
One here, yeah.
Yeah, so let's look at that unsafe block. We are creating a variable and then calling new unchecked. I suppose in that case we need everything to be inside the unsafe block.
Yeah, because this is this is even safe code, but it has a couple of unsafe calls underneath.
Yeah, and there was another case in your slides where you were doing one line of unsafe and then calling a few safe things, and I thought that just from a style perspective, another option is to essentially return a variable from your unsafe block and only perform unsafe code in there. Although
narrowing it down even more, I guess this was. So if it's in that example, that's the baby library and that's the standard library. Do your pull request. I'm totally fine with it. But I have one example before where I had. So you could argue here. You could argue, do you need to put that unsafe block next to the pointer or around the print line? And this is very much true. So I would even say, so I did it in the other example, I just put it around the pointer, which I like a lot more, because if you refactor it, that's again a segue to add. You could write a safe abstraction with that, and the other code doesn't change at all. So this would be a much, much better way of doing it. Yeah, agree. Again, if you find stuff in Bevy that you don't like, where's Francois? Is he, maybe he's ready for your pull requests.
Okay, that was it. Have a good lunch.
Thank you very much.